class we'll be discussing about dynamic modeling of bioprocess. We'll be taking a few example. One of the example is about citric acid production process, uh, which is actually we are taking from one research paper discussing on citric acid production from Aspergillus niger. So basically we want to highlight what are the main points available in this process, what are the primarily what are the differential equations they are using. We will be highlighting those aspects. It was published in Nigerian Journal of Technology. So when they are carrying out the material balance, actually one batch fermenter was considered, which is more easy in time bound data analysis. So growth model for Aspergillus niger cell for citric acid production will, because we understand here always that there are three different kinds of variables will be there. One is biomass production, one is for citric acid production, and substrate consumption model. So for growth, it is simple one, that is the differential growth expression dx dt equal to mu x. So mu is the specific growth rate. So essentially uh, in all the expression we will have the similar kind of mathematical representation for growth, but only thing is that the mu, how we are going to model, we can have choice for differential model expression. In this case the kinetic models for growth can be depending on the substrate and product inhibitor. So essentially one can be simple monode without any substrate inhibition. We will show you for some other models which are having substrate inhibition or product inhibition as well. So mu will be replaced with few other terms. So if it is monode, so you already know mu equal to mu max into s ks plus s. So mu max is maximum specific growth rate, which is a parameter here, constant rather, and ks is also half saturation constant for monode equation. So these are the two unknown parameters available which need to be determined from bioprocess data modeling. This is for monode equation. Here there is no substrate inhibition or product inhibition term available. Hilden kinetic model, which is again for mu, and you can see which is very similar, but they also assume some extent of substrate inhibition. So substrate inhibition term can be placed in denominator where it is a square by ki. So if the substrate concentration is high, then inhibition values, this a square by ki, will be significantly larger, and so the mu will be lower. So as substrate concentration increases, the inhibition will increase and the mu value will decrease proportionally, or I will say it decrease depending on the same relation how s is increased. A hyperbolic model which will include both the terms, actually one is the basic, the first term is actually the monode growth, but associated with another product inhibition term, that is kp divided by kp plus p. So if the product, that is actually citric acid, if citric acid concentration is high enough, which is inhibiting the growth, so if p is more, essentially kp divided by kp plus p, that value will increase. When p is 0, essentially that term is becoming 1, because p equal to 0, that means kp by kp is 1. So depending on how much product is synthesized, the specific growth rate can be lower with increasing product concentration. This is hyperbolic term or hyperbolic growth model. And the logistic one, logistic is very simple, because in logistic equation we assume there is a maximum concentration of biomass possible. So essentially mu equal to mu max, which is multiplied with 1 minus x by x max. So x by x max is actually the current biomass concentration and maximum possible biomass concentration. That is the nature of logistic growth model. X max is actually a parameter or constant in this analysis. X mass is also termed as carrying capacity. What is the maximum feasible biomass concentration in any bioprocess system? So essentially when x is very small, that term x by x max is nearly 0. Essentially mu will be mu max. But when the x is going to be very close to x max or maximum carrying capacity approaching, then this value is 1. So essentially 1 minus this value is 0 and mu will be nearly 0. So mu decreases as the x is increasing. So this is the 4 different variant of growth model, simply replacing the mu term with those specific kinetic model expression. We also author assumed the substrate consumption and product formation as it is proportional to the growth. So essentially ds dt, the substrate consumed, is proportional to growth term. So yx by s is actually biomass yield coefficient for substrate consumption. So this is actually parameter which to be determined in the bioprocess model. We already know this kind of derivations earlier. And similarly product formation is also they are using Ludwig-Pirate kind of model, but they have only used growth associated product formation. It is growth non-associated product formation is not there. So here dp dt rather we will say is proportional to dx dt, and this is actually product formation kinetics, but they have not used any other term which is essentially related to x, only biomass concentration, that is not there. So it is a reduced model structure for Ludwig-Pirate for product formation. So essentially we are having three different expression differential. One is for growth, another is for substrate, we have shown it is very simple enough, and another is for product. So from experimental biomass, substrate and product data, the author has modeled and estimated those parameter values. Here showing this graph for biomass growth and product formation. So here we can see for example the substrate depletion curve over here, and we can see the biomass growth and product formation. So cell concentration is shown here, which is actually decreasing at a moment finally, and substrate concentration is decreasing with time, and product formation is increasing, reaching some maximum values. So this is the experimental and model data for this kind of dynamic model equation. And finally from their result, though it is not detailed in this paper also, they established the validity of hyperbolic model. So that was actually fitting better compared to the other one. It was adapted for simulating the dynamic behavior of the citric acid production. What we don't know, because in this case always the biomass growth should increase and get stationary, but some experimental data we can see there is a drop which is not really taken care by hyperbolic model. For parameter estimated for this case was mu max, yx by s, ks from hyperbolic model. Those values was 0.013, 0.071 gram per gram and 0.001 gram per liter was the values associated with those parameters. And for parameter for citric acid production, other two terms was there. One is yp by x and kp. So kp value here is 0.257 gram per liter. So we can see in our case the maximum product concentration can go up to 3 gram per liter around, and here 0.257 gram per liter is the kp values. That means actually that kp value is much smaller than the product concentration itself. So if kp value is very smaller, that means effect of p will be higher, so inhibition is much more stronger in that scenario. So hope you understand these three different expression for biomass growth, product formation and substrate consumption. Now you all know already how to model this kind of scenario in dynamic bioprocess systems. Next class we will be discussing on anaerobic digestion using insoluble substrate for methane production. We will be discussing in next class.